The sun has been a significant source of strength for us recently in particular, and it will also undergo a critical, enchanting change in its reversal enchanting sector. This attachment occurs primarily at standard distances corresponding to the halfway point of the solar cycle. Likewise, it has far-reaching effects. Whether or not we are aware of it, it's possible that, rapidly, the sun could present a significant danger that could result in complete disruption and disaster for everyone on Earth. As you can see, the sun's attraction field is made by the movement of electrically charged gases inside. There is a process called the solar dynamo. Over the long haul, this attractive field grows in importance. Heavenly and transformed by the sun's change through transformation and convection, the end result of this cycle is a complete flipping over of the magnetic poles, the transformation of the north magnetic pole into the magnetic south pole, and vice versa. So could we dissect the entire cycle and examine the sun with greater concentration? The sun is primarily composed of hydrogen and plasma. Helium is a state of matter in which particles are not bound to electrons, resulting in a mixture of free electrons and ions. The interior of the sun is divided into multiple layers, with the center at the core, which is enclosed by the radiative zone. The center of the convective zone is the sun's most significant area where nuclear fusion takes place, converting hydrogen into helium and releasing huge quantities of energy. Above the core is the radiative zone, through which energy is transferred outward. In this area, energy moves gradually outward as photons are absorbed and re-emitted by the solar plasma. The sun's interior has an outer layer called the zone of convection, where energy is transported by convection. Plasma ascends to the surface, cools, and then sinks once more, generating convective currents in the solar dynamo process, which works fundamentally in the convective zone. A thin layer between the radiative and convective zones is important because it is where the sun shines. Shear flows in different rotational directions play a crucial role in the creation of the magnetic field. Now, for something interesting that you probably haven't heard, the sun doesn't move like a solid body. Rather, distinct regions of the sun rotate at different rates, with the equator rotating more rapidly than the poles, a characteristic known as differential rotation. Differential rotation stretches and twists the magnetic field lines, making the magnetic field stronger. The solar cycle is an approximately 11-year cycle when the sun's magnetic field undergoes a number of modifications, culminating in its poles being reversed. This cycle is driven by the solar dynamo and has multiple stages. At the beginning of the solar cycle, during a solar minimum state characterized by the absence of many sunspots and low levels of solar activity, the magnetic field is typically straightforward with a distinct north and south bipolar structure. As the cycle progresses, the number of sunspots increases. Sunspots with larger numbers are areas of strong magnetic fields and are associated with the rise of solar activity. Sunspots appear in pairs with opposite magnetic polarities and move in that direction. Over time, around the sun's midpoint, in the solar cycle, it reaches solar maximum, a period of peak activity that attracts the most solar flares, sunspots, and coronal mass ejections, CMEs. The magnetic field becomes extremely complex and tangled because of the constant bending and differential rotational shearing. As the solar maximum fades, the magnetic field begins to reconfigure itself. The reshaped and tangled magnetic field lines reconnect, and the global magnetic field gradually reverses its polarity. The north magnetic pole becomes the south magnetic pole, and vice versa. This cycle is facilitated by the advance and reorganization of solar plasma movement regions. After the pole reversal, the sun enters a period of declining activity, returning to solar minimum. Eventually, the magnetic field is rearranged, and the cycle is ready to begin a new chapter. Right now, the sun is in the solar maximum stage, and its magnetic field is about to flip. During this point, we can anticipate seeing some of the sun's activity that could be dangerous due to its captivating nature. But the reversal of the sun's magnetic field is not an unanticipated turn. Rather, like the solar cycle, it is a continuous cycle. As the sun's magnetic field advances, several things change. At the moment, the magnetic field is at its most twisted, entangled state, reaching a tipping point and beginning to reorganize itself, leading to a turn. So how do we know when the sun's magnetic field will flip? Researchers study the sun's magnetic activity, using various instruments and techniques that make use of observatories with powerful telescopes, both on Earth and in space, to provide detailed images of the sunspots and the surface of the sun. Instruments like the Solar and Heliospheric Observatory and the Solar Dynamics Observatory measure the sun's magnetic field and its changes over time. One key indicator of an impending magnetic reversal is the behavior of sunspots during the solar maximum. Sunspots appear more frequently and become more pronounced as they move toward the sun's equator, a sign that the magnetic field is becoming increasingly unstable and preparing to flip. While we're on the subject, let's investigate a little more deeply. Sunspots form when the magnetic field lines of the sun become twisted. Entangled due to differential rotation, the sun's equator rotates faster than its poles, resulting in the magnetic line's ability to bend and stretch. When these lines loop over the sun's surface, they suppress the convective movement of the sun's hot plasma interior, creating cooler and darker patches we see in sunspot images. Not only are sunspots fascinating attributes, but they can occasionally produce powerful solar flares and coronal mass ejections, CMEs. These phenomena release enormous quantities of energy and charged particles into space. When directed toward Earth, they can disrupt satellite communications, power grids, and navigation systems, and pose a threat to space travelers. Moreover, increased solar activity can enhance auroras, but it can also raise radiation levels in Earth's upper atmosphere. So, while we're on the topic, let's examine the difference between solar flares and coronal mass ejections. Solar flares are sudden, intense bursts of radiation caused by the release of magnetic energy associated with sunspots. They release a tremendous amount of energy and light, frequently in X-rays and ultraviolet light. Consider them bursts of bright light and heat on the sun's surface, resembling a massive explosion. In contrast, CMEs are enormous releases of solar wind and magnetic fields from the sun's corona, described as huge gas bubbles being thrown out into space. When a coronal mass ejection occurs, it sends billions of tons of particles from the sun into space at extremely fast speeds. While CMEs and flares are connected, they are not the same. A solar flare can occur independently, but occasionally an extremely potent solar flare can trigger a CME. Despite the fact that a solar flare doesn't necessarily cause a CME, they can be connected in terms of solar risk. Flares can disrupt radio, communications, navigation signals, and pose a significant danger to space travelers due to high radiation levels. CMEs can cause geomagnetic storms, disrupting satellite operations, power grids, and navigation systems. They can also improve auroras but pose significant dangers to Earth's infrastructure and technology. Another consideration is that during times of high solar activity, the amount of radiation that reaches Earth increases. Spacecraft and satellites are particularly susceptible to elevated solar activity. The charged particles from sunlight can damage electronic components, disrupt communication signals, and even alter satellites' orbits, harming infrastructure and technology. What else could occur to the planet? While the sun's magnetic field reversal doesn't directly influence Earth's atmosphere in the same way, changes in solar activity can have an effect. According to some studies, variations in solar radiation can influence atmospheric conditions and weather. For instance, increased solar activity can cause a warming of Earth's atmosphere, conceivably sustaining the current climate. Auroras might be the only positive sign of change we experience here on Earth. One of the most impressive effects of increased solar activity is the enhancement of these spectacular light shows, known as the northern and southern lights. These occur when charged particles from the sun interact with Earth's magnetic field and atmosphere. We often hear about the aurora borealis. However, these lights can also be seen around the South Pole. During times of high solar activity, Auroras are more common and can be visible at lower latitudes, offering dramatic shows at night. However, in addition to the stunning auroras, there are also more concerning aspects of the sun's magnetic reversal that could occur if we are ill-prepared. One of the most significant dangers posed by a magnetic field reversal is the increased likelihood of geomagnetic storms caused by the solar wind loaded with too much charge. Earth's particles interact with the magnetic field, which can, in extreme cases, cause damage and widespread blackouts. Image infrastructure is one example. On the morning of September 1, 1859, Richard Carrington, an astronomer, was observing the sun through his telescope, as he had done numerous times before. What he saw on this particular day would be remembered for being the first. At 11:18 a.m., a solar storm was recorded. Carrington saw a bright flare of white light coming from a collection of sunspots. This event, now known as the Carrington event, marked the beginning of the largest ever recorded geomagnetic storm. Carrington saw a white light that was a massive solar flare, a powerful outburst of radiation that results from the release of stored magnetic energy in the sun's environment. This flare possessed such potency that it set off a huge coronal mass ejection (CME) that was aimed at Earth. In just 17.6 hours, the CME reached Earth, a remarkably short time considering the 93 million miles from the sun. When the CME hit Earth's magnetosphere, it triggered an extremely powerful geomagnetic storm which had a quick impact and was widespread, disturbing Earth's magnetic field and the currents that cause ground-induced currents. In addition, telegraph lines, which were the backbone of global communication at the time, experienced significant disturbances. Sparks shot out of telegraph machines, operators received electric shocks, and some message stations even caught fire. The induced currents were so powerful that operators had the ability to send and receive messages even after disconnecting their batteries. One of the most striking and noticeable effects of the Carrington event was the brilliant display of auroras. The auroras were so bright and widespread that they were visible in a way that was not typical. People living as far south as the Caribbean, Mexico, and Hawaii reported seeing the sky illuminated with vibrant colors. The auroras were so vivid that they lit up the night sky, allowing people in the northeastern United States and the Rocky Mountains to read newspapers by their light. Gold miners in the mountains were reportedly awakened by the brightness, mistaking it for sunrise and beginning to prepare breakfast. The crowd referred to the sky as having hues of purple, green, and red that shone, moving across the sky and shimmering. Now imagine if a solar storm of the magnitude of the Carrington event were to arrive on Earth right now. The results would be disastrous. The sun is undergoing significant change, a method for reversing its magnetic field that happens roughly every 11 years as part of the solar cycle. This event, driven by the solar dynamo, could have far-reaching consequences for Earth, having the potential to cause disruption and catastrophe caused by the sun's magnetic field, generated by the movement of gases with electric charges inside, creating an intricate magnetic field that ultimately reverses the sun's primary material, the polarity plasma of hydrogen and helium, containing energy derived from nuclear fusion at its heart. This energy is transferred outward through the radiative zone and then by convection in the sun's outermost layers. Dynamo system, which operates in both the convective zone and the tachocline, producing a differential magnetic field of the sun's rotation, where the equator stretches at a rate faster than the poles and amplifies the lines of the magnetic field. Presently driving the solar cycle, the sun is at its solar maximum, where solar activity and sunspots are at their peak, potentially causing risks like CMEs and solar flares that can cause disruptions to satellite communications, power grids, and pose a threat to scientists and astronauts. They monitor the sun's magnetic activity and predict sunspot behavior when reversals in the magnetic field will occur. Sunspots, which result from tangled magnetic lines, can produce solar flares and CMEs, both massive releases of energy that have a variety of effects on Earth, while CMEs release vast amounts of solar particles into space. Solar flares release radiation. These phenomena can enhance auroras but also pose critical risks to Earth's infrastructure and technology. The way the sun behaves is a fascinating interaction between nature and physics. It's a phenomena that affect more than just our solar system, but also Earth's life. Comprehending the solar industry's complexities and activity is important, especially now that we continue to rely on technology that can be impacted by solar events. The sun generates energy through nuclear fusion, converting hydrogen into helium, and producing enormous amounts of energy. This energy moves through the process through the various layers of the sun, eventually reaching the surface. Solar activity can send radiation into space, manifesting in numerous ways, such as solar flares, sunspots, and coronal mass ejections. Sunspots, called cooler areas on the solar surface as a result of magnetic activity, appear as these dark spots, changes in the capacity of the sun to activate an approximately 11-year cycle, known as the solar cycle, which includes high-activity solar maximum followed by calmer periods solar minimum. During the solar maximum, a rise in the number of sunspots causes solar flares to occur more frequently. Additionally, solar flares caused by CMEs are brief outbursts of energy that release radiation across the electromagnetic spectrum. Comprised of X-rays and ultraviolet light, these rapid flashes can have an impact on radio communications and pose risks to astronauts in space. CMEs, on the other hand, are massive eruptions of rising magnetic fields and solar wind from the solar corona and are released when directed toward the planet Earth. These ejections can cause geomagnetic storms that wreak havoc on the planet's magnetic field, bringing beautiful auroras, but also the possibility of interruptions to technology. The effects of solar activity transcend space, influencing Earth's atmosphere and surface. Studies suggest that variations in solar radiation can affect climate patterns, potentially contributing to weather anomalies. Increased solar activity can also lead to atmospheric warming, which is a significant component in discussions concerning climate change. The possibility of technological damage because of solar storms cannot be understated. A severe geomagnetic storm could disrupt electrical grids, affect satellite operations, and damage navigation systems. Preparing for such events involves keeping an eye on the sun's activity and developing strategies to reduce their influence on infrastructure. Researchers continue to study the sun's magnetic field and its cycles to better predict when significant solar events are possible. This study involves a combination of ground-based and space-based observatories tracking sunspots, measuring magnetic fields, and analyzing solar wind. With advancing technology, our ability to predict solar activity improves, which is essential for safeguarding our technological infrastructure and ensuring the safety of astronauts as we explore the universe. As we study the sun's impact on Earth, it becomes increasingly evident from the breathtaking displays of auroras to the possible difficulties posed by solar storms. The sun is still a powerful force in the solar system we live in. Comprehending its cycles and actions not only expands our understanding of space science, but also enhances our preparedness for the impacts of solar activity on modern life.